Hi, my name is Xiaochen, PhD student from UC Riverside. So I'm the first one to present it this morning. Thanks for getting up so early. So my previous project, SyzScope, revealing high-risk security impact of Fuzzer-Exposed bug in Linux kernel. So fuzzing is still the best way to find bugs in Linux kernel. So how does fuzzing actually work? So Fuzzer generate a bunch of test case and feed to the kill email, which running the Linux kernel. So if one test case finds it's crashed the kernel, then the Fuzzer will capture those output from the kill email, generate a bug report, and report that bug, that thing as a bug. So we have some case-on bugs, some warning bugs, general protection fault info, or some other bugs. So bugs can be simply categorized into kernel sanitizers and kernel assertions. For example, the kernel address sanitizers aim to capture specific type of bug, like memory error. And kernel assertions is just some instrumentation in the kernel. For example, this value should never less than 0. So the developer could add a check to check if this value is less than 0, then we can throw a warning. General protection fault is more about when you access, for example, user space memory, or you write to a read-only data. And some other bugs that cannot be simply categorized, then they fall into the bug. So they just start with a huge bug. OK, different bug types have different security impact. Memory write bugs has the severe security impact that probably could compromise the entire kernel. For example, by overwriting the UID, GID, or overwriting the function pointer, the attacker could grant the total control of the entire system. So we think the memory write bug is fair enough to claim that it's a high-risk bug. And we have invalid free. So invalid free equals to the double free. So it basically creates a use after free, because it's free twice. So we claim that the invalid free is also a high-risk bugs. Besides that, we have memory read bugs. Memory read bug is sometimes very useful because it's leak sensitive information out of the kernel space to the user space. Like we can leak the KSR offset or some other sensitive kernel address. But just using the read capability, we cannot exploit the kernel. And we have some other long security bugs like warning, info, general protection fault, and bugs. So they are long security bugs, and they cannot just directly exploit the kernel. So we think the memory read bugs and all the long security bugs, we think they are low-risk bugs. By saying that, we mean by using their capability, showing their bug title, like read, like warning, we don't think they are strong enough to compromise the kernel. The first problem for the fuzzing, the Linux kernel bug is that there's too many bugs to fix. syzbot is the world's largest Linux kernel fuzzing platform. It reports more than 4,000 bugs in the past 4 years, and it constantly reports several bugs every day. So you can see there's still like 1,000 bugs waiting to be patched. So you can imagine how much stress that put on the developer's shoulder. So we can automate the bug discovering process, but in terms of the bug fixing, we still rely on human work to fix each bug. So in such case, a prioritization of the bug fixing is becoming something realistic. For example, the high-risk bug need to be fixed as soon as possible, but the low-risk bug, we can wait until someone is free to fix them. So for example, we can see the average fix time of use after free read bug is 83 days. As for the UF write bug, is only 37 days. The same theory applies to the out-of-bound bugs. So the write out-of-bound bugs is only 29 days, but for the read out-of-bound bug is 89 days. So there is some sort of prioritization to put the limited resources on more urgent bugs. So it's a great strategy for the limited resources. So there's a bunch of low-risk bugs, and there's a bunch of high-risk bugs. Let's fix those high-risk bugs this week. And we can probably, it's fine to leave those low-risk bugs for next month, because they probably just like affect the performance at least it cannot just exploit the kernel, so it's fine to leave it for the future. But what if some low-risk bug turn out to be high risk? Okay, the consequences could be really bad. But the reason is why. Like, how could this happen? To understand why some low-risk bug could be turned into high risk, we have to understand the underneath mechanism of fuzzing. So as we know, fuzzing sends test case to the kill email. And in such case, on the right-hand side, you can see there's a tree. So in this case, it's a warning. So imagine we find this warning. And we find a warning, what do we do now? The father said, OK, stop the execution and report it immediately. So, but you can see there's clearly two other impacts and more strong impact right behind this warning. We have a double free, we have a UF write. So, but stop the execution and report, which means the warning will just crash the kernel. The execution will just stop at this warning. So what about those more critical impacts? The father have no idea they exist. So the father just report this warning to the upstream or to the syzbot. So this bug is labeled as a warning. So that's a problem. Fuzzing only presents the first impact of a bug, but the first impact may not represent the most critical impact. So let's define the high-risk impact and low-risk impact. We already know the UFOB write bug and invalid free are high risk, but we have some follow-up impact are also considered high risk, like control flow hijacking, which means the attacker could control the function pointer, and the arbitrary constraint value write, which means the attacker could control the what value write to this memory address. The arbitrary constraint address write means the attacker could control the address that a value write to. OK, so those three follow-up impact cannot be found by the fuzzer alone. So we have to use some advanced program analysis tool to achieve that. And we will see the reason in this slide. OK, here is the dummy user free functions. We just allocate a function and we free it, and then we use it. So easily, this kernel address setter could capture this user free read. But you may say, OK, in the last example, we just stop at the first impact. What happens if we just let the execution continue? Probably we will find this control flow hijacking in here, right? Because the oops has been freed. And so the value in the oops could be controlled by the attacker. Then the function pointer was dereferenced. The father should capture it or not. Let's see what happened in this line. When we assign this array, the index 0 in this array to the function pointer, it's equals to just dereference this data pointer. But remember, this oops pointer is come from a freed memory. So the father cannot control the content of this freed memory. So this oops could be any value. For example, if it's 0, then the kernel panic. It triggers the null pointer dereference. Or the data pointer is some like non-memory value. When they dereference this data pointer, it still crashes the kernel. So oftentimes, at this line, the kernel just crashed. Then we will get nothing. The execution will just stop. So, but imagine how a real-world attacker to exploit such vulnerability. They use Heapspray. Heapspray managed to control adding bytes on this freed memory. So is there any technique that's similar to the Heapspray, like in the program analysis field? Yes, it's symbolic execution. And that's how SyzScope to simulate this Heapspray process. We symbolize the entire free memory. And so in this line, we can capture this. OK, it's read from a free memory. Then we identify this UAF read. And in this line, it dereferences a symbolic data pointer. It's fine. It's symbolic value. It doesn't have any concrete value. So it doesn't panic anything. And the function comes from a symbolic data pointer, which the symbolic value propagates to the function. So the function pointer is also symbolic. And finally, we're dereferencing a symbolic function pointer. This is captured by the symbolics engine. So we know that it's a control flow hijacking. And this is the workflow of SyzScope. We have the first section is the fuzzing. We provide more context for the further static analysis and for the symbolic execution. So there's a lot of dirty technical details behind, but we have limited time, so I don't want to jump into too much details. So there's like how we apply the entire symbolic execution on the kernel and how we use static analysis to mitigate the passive explosion problem. So if you're interested, you could read our paper, but there's not. I try to write all those codes to explain this, but we just don't have that much time. So let's jump right into the evaluation. So among the more than 1,000 valid bugs from the syzbot, this is our data set, more than 1,000 bugs, we find actually around 20%, 183 bugs, that low-risk bugs that they can be turned into high risk. So in the past 4 years, syzbot only find around 170 high-risk bugs. So we already doubled the number of high-risk bugs. And 15 of them, they are actually high-risk warning and info, which means those warning and info have at least one high-risk security impact. And 17 of them, they are general protection fault and bug. And among those 183 high-risk bugs, we find 179 counterflow hijacking, which consider the top risky capability. Here's the breakdown of all the capability we have, and we find I highlight some data like the arbitrary address write, the arbitrary value write, the counterflow hijacking, the invalid free. So we disclose our finding to the CVE maintainers, and we got some CVE assigned, and we are happy to see that when the CVE assigned, several downstream distributions patch this vulnerability immediately. At least we're happy to see we make some contribution to the community. And that's all for my talk, and ready to take any questions.